Cool, guys. Welcome. Most of you look kind of sort of awake right now, end of the day. So welcome to my talk, ML versus Cryptocoin miners. I'm going to go on a little bit of a soapbox here in a minute about why machine learning is a dumb term, and what I'm actually doing is just stats, statistical analysis, nothing special. But a quick about me. My name is Jonn Callahan. I'm a principal appsec consultant at a boutique consulting firm based out of DC. We do a lot of work with a lot of different people. We work with a bunch of different FIs, banks, insurance industry. We're all over the map. I personally, like, my bread and butter was AppSec, but I also lead our cloud practice. I do a lot of container security with Kubernetes and OpenShift and Nomad and all that good stuff. Also a huge Python fan. That's really my bread and butter is Python, but I've recently transitioned to Golang too, is kind of like my alternative. I need something to run fast. I need it to run everywhere. All right, in Golang. If I need to write something quick, write it in Python. Or if I'm doing any data science or any math or anything like that, I'm doing Python. I do really like math. Math is really cool. I am terrible at it. I like to call myself a mathematical skid because most of what I do is I just plug and chug through NumPy, and I let that handle all the heavy lifting for me. I don't really know what I'm doing half the time. I'm also a big metalhead. If anyone out there likes metal and wants to come talk to me afterwards, yeah, okay. So machine learning's cool. I think so. There's going to be a lot of graphs and stuff. So to lighten things up beforehand, we're going to do a lot of memes. So artificial intelligence is dumb. And I mean, this is tech companies in a nutshell. If statement is it machine learning. Pulling the hood off of a big if-else letter, artificial intelligence. This is me on the left, a real-life picture from a couple years ago of a data scientist that bastardized something or other. I'm not a very good software engineer, and I'm not very good at math, so I'm kind of a half-breed muggle of sorts or something like that. This was my personal favorite. Because, again, I am terrified of math and not very good at it. So yeah, let's get into it a little bit. So as a quick intro, so the whole idea of this talk is to kind of build a very niche IDS kind of solution in terms of finding cryptocoin miners within an AWS architecture. So within the last couple of years, I'm sure everyone here is well familiar with Bitcoin and all the other alternative coins that have come out. While it provides a lot of different things, what it's really done for the Black Hat community is it's given you a very direct path from server compromise to cash payout. I don't have to worry about trying to sell out your server to a botnet farm or something like that, or doing click farming or anything like that. I can compromise a server, turn on a miner, and then immediately start reaping profits off of it. So it's become a huge attack vector, or not an attack vector, but a huge issue from servers that have become compromised. That's what happens to them. And all of a sudden, their CPU gets throttled, your RAM goes through the roof, and your server becomes underperforming. So I went and started looking specifically at Monero and Varium, Varium is pretty much dead now. It's a dead coin. I started this research a while ago, specifically because they're CPU mineable coins. And again, I'm working within specifically an AWS architecture. And the reason I focus on CPU-specific coins is because preventing GPU mining is really easy. Just don't let GPU instances run in your architecture or in your environment. Like, I can almost guarantee you, like, 99% of you out there have no legitimate reason to have a GPU instance running. Just block it. I mean, just use the IAM policies and don't let it run. You're done. It's not a threat anymore. So I really wanted to focus on CPU stuff. What happens if your M5D large gets compromised and starts running a Varium miner or a Monero miner? So that's one part of it, why I wanted to look into this. The other piece, too, is AWS uses what's called VPC Flow Logs. I'll get into a little bit more of what flow logs actually are. Suffice to say, they are packet captures to a degree of the network traffic that's going in within a particular VPC. If you're not familiar with AWS, a VPC is just your VLAN. It's your virtual private something. I can't remember what the C stands for. It's your VLAN. So you segregate into your subnets and whatnot. So mining traffic is also very pattern heavy, pattern rich, and which makes it an excellent candidate for using different techniques to try and flag it as opposed to flag it out from what would be considered normal traffic or not mining traffic. So I wanted to look in and see if it's possible to build an IDS. It's not really an IDS. I'm just looking for one particular thing. It's also worth noting that if you are familiar with AWS, there's this thing called guard duty that will supposedly do this for you. It will check to see if you have any miners running on your network. The only thing it's doing is checking domain name lookups and checking against a known bad IP list. That's it. So all you have to do to get around that is just set up a mining pool on your own domain. Set up your own private mining pool that hasn't been flagged as a bad IP, that's not using a publicly known domain name, a publicly known mining domain name, and you're done. You've just bypassed guard duty. That was easy as that. So I wanted to build a more robust solution that was built upon the traffic patterns itself instead of something just as a key value lookup. So I sent about and started collecting data because, I mean, when I'm doing any kind of like pattern recognition or machine learning type stuff, you have to build your data set to begin with. So I went and took 12 different Cryptocoin miners, stood them up on a variety of different C4 instances. They're large through their like 4x large or whatever the largest one is, one of each. And started up a Monero miner and just let it rip for 24 hours and captured the VPC flow logs and just made a note of the private IP of each miner, or the public IP of each miner within the VPC. I also got lucky enough. I spent a couple of weeks like going into every Slack channel that I'm in, begging everyone I knew who was within AWS. I was like, can you please just send me your VPC flow logs? I promise I'm not going to do anything with it. I know it's kind of sensitive, but just give me your data. Finally, someone was willing to give me a good chunk of their VPC flow logs. They just dumped the whole bucket to me. It was really generous of them and pretty much enabled all this research. It was about 3 weeks worth of traffic, which turned out to be about 1,000 different machines, which 38,000 different unique connectivity streams across those 3 weeks. So if those three metrics at the bottom don't make any sense, we'll get into that in a second. So VPC flow logs, what they are is they're aggregate 5-tuple PCAPs. So your typical 5-tuple PCAPs is your source IP address, your destination IP address, your source port, your destination port, and the amount of data sent, or rather the packet itself. In this case, what AWS does is it aggregates all the traffic that occurs over that unique connection between each source IP import and destination IP import, and then collects the amount of packets that have been sent and the size of the packets that have been sent. And over those 10-minute windows, it dumps that aggregate into either CloudWatch or an S3 bucket, which again provides an interesting challenge because I don't have raw PCAP data to work against. This is a good thing because I know I can build my models using far less data. Instead of having to work off of hundreds of gigabytes worth of PCAPs, I can work off 1 or 2 gigabytes worth of VPC flow logs. But it also provides a unique challenge in that I have to go back and rebuild the TCP streams, since you end up with 2 log entries for each TCP stream because TCPs are bidirectional. You have 1 for each direction. But the VPC flow log looks like this. It's a simple space-delimited single-line entry broken down with the second to bottom line gives you what each field's definition is. Most of that is pretty irrelevant to us. But the things that are important, again, are the IPs, the ports, the packets, and the amount of data. So the first thing we can do is just filter out anything that has reject on it. So that second to last field there, that action is either reject or accept. And the reject entries happen when a network connection is tried to establish, but is blocked by either a NACL or a security group. So if I try to SSH into a box that doesn't have a public security group, it'll generate a reject VPC flow log entry. Or if I try to get out of a network and there's no, there's a NACL that's blocking it, it'll get filtered by reject. So since I'm looking for active mining traffic, it's very easy just to filter all that out right away. I don't care about blocked mining traffic right now. I'm specifically looking at actively mining traffic. The other thing I can filter off right off the bat is the protocol field. So that's the 5th to last one. That 6 and 3, that 6 right there is the protocol. 6 corresponds to TCP. So I want to look for all the TCP entries. So again, I just dump and ignore every entry that doesn't have a 6 for the protocol. And right off the bat, that filters out a bunch of my traffic. So that makes things very easy to just cut out a lot of the noise. So originally I was going to organize by IPs and ports as opposed to just IP addresses when rebuilding this. The problem is that due to the ephemeral ports on the client side of the connection can cause issues. So over the course of a 10-minute period, a mining client might end up using 3 different ephemeral ports, which can break the pattern recognition unless I'm able to rebuild and say, okay, I was using this ephemeral port for 3 minutes and this ephemeral port for 4 minutes and this third one for another 3 minutes, which is a pain in the ass to aggregate and requires a lot of CPU processing power, or a lot of processing power. So instead, I just aggregated things by unique IP addresses and just analyzed things that way. And then I also, in order to make sure I was treating the same thing as a source, I went and checked to see for each IP address, was it an AWS-owned IP address? If it was, I treated that as a source. Or if it was a private IP address within the AWS IP space, or a private IP address in the private IP space, I treated that as a source. And from there, I went and rebuilt everything and re-aggregated each VPC flow log entry. So the last piece you have to do, which I probably should have included on here, is you also see there's a start and end field, the third and fourth to last field. You can use those to actually correlate which 2 entries belong to the same TCP stream at a given 10-minute interval. So you take those, you glue them back together, and now you have the total data sent across one TCP stream over 10 minutes. And then after all of that, you actually have some working data to work with. I can go back and say, all right, for the first 10 minutes this box was online, it sent 100 packets to this IP and received 30 packets to this IP. Over the next 10 minutes, it sent 40 packets and received 20. And from there, I started building out my data set, or started building out my models. So there's really, from all that information we have 8 different features that we can extract. The number of bytes that are sent, the number of packets that are sent, the number of unique source and destination ports, which I didn't end up using for anything, but it's there if I need it, and then the actual length of the communication. Which, again, the length of communication I didn't really use for anything either. I focused primarily on the number of bytes and packets that were sent. And my general strategy was to just graph the data and eyeball patterns and just see like what stood out to me. What can I quantify and find, turn into an algorithm or function and filter against everything else. And then I would just, as I would build these models, I'd go back and run all of my test data through it and see what got passed. If all my test data was coming back and saying, oh, this matches this model, it's not a good model. So I'd go back and look at something else. So attempt 0 was just to look at the number of unique destination ports. The idea being that if a client was interacting, or a compromised client was interacting with a mining client, it was always going to interact with the same remote port, such as 5555, 6666, whatever, the usual mining ports, if you're familiar with that at all. And as well as the fact that there'd be a lot of ephemeral source ports. This didn't really work too well, surprisingly. It turned out that in my test data, the destination IP addresses still ended up with a lot of single-digit port numbers, or not single-digit port numbers, but the number of unique ports to use were 1 or 2. So this didn't actually end up being a very good strategy. So I just went back to the drawing board and tried again. I actually had a lot of failures. I don't include all of them here, or we'd be here all day. Moving on. I went and tried to, again, graph my data and actually see what was going on with it. Is there any kind of clustering? Is there any kind of, any discernible patterns that I can make out from the data itself? So graphing them out. This is a couple of them. I think it's only like 6 of the actual mining clients that I sent out, looped over through a GIF. On the x-axis, you have the number of source bytes, and then on the y-axis, you have the number of source packets. So just looking at this, we can already tell there's some strong patterns going on here. For one, there's a strong linear correlation between all the data. It follows a pretty straight line pattern right up the board. On top of that, there's also some striations that are being built in there. These like clustered lines of points. I think I can pause this. Yeah. So you can see there's these striations that are coming up through the pattern, through the data, which is like, that's probably a pretty unique pattern. You're not going to see that in just other randomly generated network traffic. So that's probably going to be a really good thing to work against. However, trying to quantify that's a little bit tricky, and trying to quantify that and then build a model off of that runs quick is even harder. So I set that aside for the time being. If we look at the destination metrics, again, we see some correlation. It's a lot looser. They're not hugging a straight line nearly as tightly as the other ones are. But again, you do get what looks to be kind of like, not a striation, but like a honeycomb pattern. So again, we're seeing some sort of structure to this data, which is a very good thing. Structure is what we want. Structure is what lets us filter out noise. And this is for the destination bytes and source, or destination bytes and packets, rather. And then if you go through and you map out the opposites of that, so the number of source bytes versus the number of destination packets, you don't really get much of anything. Again, patterns, whoops. You get the same kind of honeycomb pattern, but not nearly as tightly. Oh, no, this one is where you get it. Yeah. So you get the same kind of striation / honeycomb pattern going on here as well. But correlation is not there really at all. You're getting much more closer to an oval than anything else. And then the same goes for when you swap it, you do source packets versus destination packets. So suffice to say, we do have something to work off of. We've got some strong clustering and some strong, very clear linear regression going on between all this data. The strongest between the source packets and the source bytes, but clearly not between all of them. Again, we also have the striation pattern occurring. Weirdly, I didn't point this out before, there's also points at 0, 0. You might not be able to see this, but down here in the corner, there are points at 0, 0, which is a little bizarre. What that's telling me is over a 10-minute period, for whatever reason, my client wasn't sending any packets or any data for 10 minutes straight. It's likely that the pool went down for a period of time, and it's not actually 0, but very, very close to it. I don't actually know. I didn't monitor these miners at all. I set them up and set an alarm on my phone for 24 hours to come back and turn them back off. I didn't watch them at all. You can also set up like backup pools when you're mining. So if your pool does go down, you switch to another one. But I explicitly didn't want to do that. I wanted to mine against the same target for a long period of time to get a very clean data set to work against. Suffice to say, I don't know why that happened, and I haven't gone back to really investigate it at all. It does come back to bite me in the ass a little bit. So building a model. First thing I did was focus on the clustering. So we have some very strong clustering going on the source metrics. And so what I decided to do was build a convex hull. Is anyone here actually involved with machine learning or data science at all? 2 people. Cool. So this is kind of similar to a one-class SVM, except I built this before I knew what a one-class SVM was. So I built a convex hull. I should probably go back and fix that. So essentially what I did was, if you don't know what a convex hull is, if you take a point cloud and you draw the hull around it, you have a convex hull, as opposed to the concave hull. And again, I didn't implement the math for this. I called scikit.convex hull and then passed my points in, and I got a hull back because I'm really good at math like that. So what I did is I took those points and I built a convex hull around it. And I used that as my first model. And I started taking my test data and was feeding it through this defined hull to see, all right, what kind of test data do I have that exists within this hull that I've defined, this polygon. Did the same thing for the destination metrics. So I come back. I didn't do 100% member, so I operated against membership rate. So when I took a set of test data and passed it through here, I checked to see how many of the points relied with, or how many of the points were within the convex hull itself, and defined that as the membership rate. I didn't want to do 100% membership rate and rip things out if they weren't 100% because I didn't want to have it cause any false positives. So I picked 98% completely arbitrarily just to see what would happen. So with a 98% membership rate, I have a slide out of order here. Awesome. Well, so what I'm actually doing isn't two-dimensional convex hulls like these graphs indicate. They're actually four-dimensional. I built a four-dimensional convex hull, which I can't graph because we live in a three-dimensional world. But because defining a convex hull depends on Euclidean distances, you can define a four-dimensional convex hull which is exactly what I did with both the source and the destination metrics, and then fed all the test data through that, as opposed to building 2 separate models and then running things through it twice. I have one model and run it all through once. This works in really low dimensions. I'm only using four different dimensions, so that makes things really easy to do. If you ever try this technique against like real data sets that like data scientists work with that have like thousands of dimensions, this quickly falls apart due to what's called the curse of dimensionality. So if you're ever getting into this at all, I would highly recommend looking that up and being aware of that anytime you're trying to build any of these models. The curse of dimensionality basically states that as your dimensions linearly increase, the amount of data you need to properly represent that field increases exponentially. So you need a lot, if you have 100 dimensions, you need a lot of data to properly represent the space within all 100 dimensions. Because I'm working in 4, I don't really need that much, so it works out fine for me. So running it through, I end up with some false positives. I'm sorry, this is a true negative. So this is an example of a data set that got filtered out. So this is a set of my test data that came back, and it had under a 98% membership rate. And I mean, just looking at this, you can just tell the points are nothing like what we saw for the mining data itself. This is clearly something very different. And we came back, and I filtered 38,000 streams down to 19. Not nearly as good as I was hoping it'd be. That's a 50% success rate. That's terrible. I mean, it's not bad for a first try, but overall, 50% is not good. You can't do anything with that. So I went through and started to look at what actually got through, what kind of false positives I got. This is a false positive. As you can see, this also looks nothing like the other data we had. It's a single point that's sitting down by 0, 0. But because it lies within the convex hull, it passed. And it got flagged as mining traffic, which is clearly a problem. So going through, my quick and dirty hacked fix for this was just to strip out all zeros. All points at 0, 0, or technically near 0, 0. I just went and I just ripped it out, and then I rebuilt my convex hull. So that same false positive that got through last time was trimmed out just by me redefining a convex hull that wasn't including all those points down by 0. And that did the trick. I mean, that went through, and that killed everything from that last 19,000 streams that had gotten through. I got down to 4. Not 4,000, like literally 4. And all they are just single points that are sitting inside the convex hull. Or not single points, but they're actually stacked. There's like a couple hundred points, probably from some protocol that calls out and calls back regularly every so often. With the same data and the same response, something like NTP or something like that. So again, this looks nothing like our mining traffic, so this is really easy to strip out. But this first pass wasn't sufficient. So from there, I have a lot of options. I kind of sat down and just kind of like brain dumped a lot of different things I could go off from there. Some different things you could do is like the size of the actual hull itself. So if I was to go through and look at the size, if I was to define the convex hull for those single points, it would come back as being at or near 0. That's obviously a very big difference from the size of the hull of the blue area. So that right there would automatically filter those out. You could also do the mean, median, nearest neighbor, which is for every point you find the closest point to it, and then you average those distances together. That gives you your mean and your median, those distances. And those give you your nearest neighbor metrics. That would obviously work very well as well. Spatial homogeneity, which is basically just quantifying how evenly distributed the points are across a given area. There are functions to do that, the Ripley K and L functions, but they're expensive. And they're also not implemented in NumPy, which means I have to write it myself, and I don't want to do that. So an alternative idea I had was just to build a bunch of concentric circles off the centroid of the cluster. So if I was to take, if I was to find the centroid of this, probably somewhere around here, and then basically build a set of concentric circles with its center sitting at that center of this, the center of this cluster of points. and then find the number of points that are within each circle, I basically get a hacked together quantifiable metric of how evenly distributed the points are. If the points are all very skewed to one side, you're going to end up with a line graph that's very spiky versus very smooth. Again, there's also the striation stuff. I honestly don't know how I would quantify the striations there. I've whiteboarded a couple different solutions, and all of them are pretty bad. So I don't know how I'd even go about doing that. Timestamp analysis, so actually going back and looking at how the data changes over time, instead of looking at aggregate packets. So I'm looking at 3 weeks of data at a time, or 24 hours of mining data at a time. It would probably be better to look at that, treat that data as it is, as temporal data. It's data that I'm receiving at 10-minute intervals, and start treating it as such. Watching how the data changes every 10 minutes as I get a new VPC flow log entry in my bucket. And then there's the usual linear regression stuff. So actually performing a linear regression as opposed to just eyeballing and saying that there is a correlation there. So I spent like an hour or two today actually playing with these, and I went through and I did the how the convex hull changes over time. This is kind of my attempt at the temporal analysis. So the idea was to take every set of VPC flow log entries, and every time I got a new entry, I would recalculate the convex hull, find the area of that, and then chart it. So you can see over time the area grows, obviously, because as you get more points, you're more likely to get points that create a new edge or new plane on your convex hull, which creates a larger area. The reason it flatlines for so long, well, actually, I don't know why it flatlines for so long. This has to do with the scikit tool I was using to actually find the convex hull was throwing errors when I was using too few of points. So I threw it in a try catch, and then I just passed the exception, and then that was it. I didn't actually investigate why that was happening. But you can still see that over time, the area of the hull grows. My guess is because the points I was selecting were too close together, it couldn't accurately find, because they were too similar, it couldn't do the proper floating point calculations to figure out where the edges of that convex hull would be. So once it had enough points that were far enough spread out, it was able to finally find a convex hull of sufficient area, and then and then going forward, it could obviously keep finding it. But as you can see, they're not super similar. I haven't graphed it out as how that compares to other traffic, but they follow a somewhat of a same pattern. The big thing to note is that there's a lot of flat areas with large spikes. So you're not seeing regular steps at any kind of intervals. What you're seeing is a lot of smalls and then a big jump, and then a lot of small and big jump. And that's probably due to how the Cryptocoin miner is finding a share and submitting it to the pool, because that's going to require a lot more traffic. And as that requires more traffic, you're going to end up with wider points outside your metrics, build a bigger hole, and you're going to get a larger area. The other one I did was the concentric circle ones. So basically, I went through and found the centroid of each set of mining traffic, and then calculated the number of points. So on the x-axis is the distance from the centroid, and then the y is the number of points. So as the radius increases from the centroid, you're obviously going to have more and more points that are within that circle. And again, this follows pretty much the same line. And this would probably be a good and cheap metric for determining spatial homogeneity, like how distributed are the points? Are they relatively evenly distributed, like they would be in this graph? Where if something were much more dispersed, you'd probably find something where you have a lot of sharp peaks and then plateaus, as opposed to something with a nice, smooth, almost logarithmic looking curve. So those are the two I tinkered around with today. Other things I would need to do is optimization. I've been running this on my rinky-dink laptop, my 2015 OS X box. It gets through everything in like, it'll build the model in about 60 seconds, 90 seconds, and then it'll run through a gigabyte's worth of VPC flow log data in like 5 minutes, which honestly isn't too bad for just a crappy laptop. You could easily throw this on like an M5 large and get 10 times the performance out of that. It's also single-threaded, which isn't the end of the world since NumPy is doing a lot of the heavy lifting. NumPy is just a direct hook into LPAC or LAPAC and BLAS, which are already multi-threaded and multi-core, so that you're using most of your CPU to begin with, but you could probably optimize it a little bit more. I also need to go back and actually benchmark how long these took. I should have timed it while I was already in there doing it, but I forgot to actually call that and see how long it's taking to actually generate this data, as opposed to generating, say, the convex hull. And then collect more data. I mean, I need a lot more data. Mining different coins would be interesting, although I don't think that'll make much of a difference because it's all built on top of the Stratum protocol. Different reward systems, which is how pools like pay out your share. Like you found a share, you spend a share, you get X amount of Bitcoin or Ethereum, whatever you're mining. The way that's how much you get is determined. There's a couple of different systems. I don't think that'll change anything, but it's worth tinkering around with. The big one to look into is solo mining. Solo mining generates very different looking traffic. I actually have some data. I just haven't started working with it yet. I've graphed it out, and what you actually end up with is 1,000 points pretty much all on top of each other. You get very, 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 very tight clustering all around the same area. Not even like a linear regression line, but around like the same very small area, you get points stacked on top of each other, which again should make things pretty easy to fingerprint. As well as rejected traffic. Rejected traffic, again, would probably be pretty easy to fingerprint because it's basically Stratum calling out every 10 seconds, making an API REST call and saying, hey, are you alive? No, blocked, come back. It'll sit for 10 seconds, it'll make another one. It's just going to repetitively do that. So it's going to have a very, very structured and predictable pattern that'll be pretty easy to flag. And then I need more test data too, like actual VPC flow log data. So if anyone wants to donate any, feel free to come talk to me so I can get this ball rolling a little bit more. You also, if you guys are heavily involved with AWS and you're aware of Reinforce that happened earlier this week at all, you probably saw that we now have span ports as a service. They're calling it traffic mirroring. What you can basically do is take a source ENI, an Elastic, it's a virtual NIC. You can take that and say, I want to mirror this traffic to somewhere else and point it to another ENI. So you can get true PCAPs off of that. Like you can run Bro on top of that or Splunk or whatever it is you're doing, whatever the file beat version of that is. So you can get like more traditional network monitoring tools hooked into AWS now, as opposed to relying on VPC flow logs, which are unique for AWS, requiring very special tooling. The downside is it's pretty expensive. I mean, $11 a month just for a single network interface. You're gonna have to if you want to make that economical, you're either gonna have to be very specific about the things you're looking at, or you're gonna have to you're gonna have to re-architect things so you end up with like you use proxy servers to tunnel all your traffic out. And even then, you're still probably gonna miss things, because what happens if something behind the proxy gets compromised and you're not watching those logs and it's making requests that don't go through your proxy. So it's nice that you have it, but it's pricey, and it's probably not going to end up replacing flow logs as the end-all be-all network monitoring solution for AWS. The other downside to span ports as a service, as I'm calling it, you get a lot more data, which is a good thing. You have a lot more data to work with. You can build far more accurate models, but because you're generating, you have every packet captured as opposed to just a single line entry representing 10 minutes of network data, you very, very likely end up with terabytes of data versus gigabytes of data, which means the models you build are going to need much more resources to process and actually churn through all that, unless you have some very strong filtering mechanisms to start kicking stuff out. So there's some pros and cons to it. But yeah, for the tooling and stuff, I built it all with Python, NumPy, and SciPy are the two. I also use scikit-learn. I think I used sklearn for something or other. And then matplotlib was for all the charts. If you're at all interested in like data science, not even data science. If you're interested in like how math beats security, or how like something like Netflix builds a recommendation engine, I highly recommend this book, Algorithms of the Intelligent Web. It's like 130 pages long. It's really short. The only prerequisite knowledge you have is Python. Do you know Python, and did you graduate high school with, like, take math in high school? Like, the prerequisites for it are pretty low. I will say the Python syntax is more advanced. They use a lot of the more advanced NumPy features, like all the ND array slicing is something that I wasn't very familiar with, so I had to go and spend some time learning things on the back end, but it's a very good intro to this kind of stuff if you're at all interested in it, which I think every blue team operator should start digging into these things and start building their detection engines around these kind of principles as opposed to just rules, simple rules, rule checks. And again, if you're feeling generous, I need VPC flow log data. So if you're feeling like donating, I'm even happy to work with you and try to figure out a way to sanitize it. Like just doing a match replace on all the IP addresses and ports. Happy to do that. I have a proof of concept for that already. So yeah, come talk to me if you are. I also plan to release this at some point. I have some sample code out right now on my GitHub, but it's terrible. Don't go look at it. It's really bad. But I plan to make a soups and nuts release that'll basically, you just point it at an S3 bucket with VPC flow logs, and you can just let it rip. You can deploy it wherever you want. And if you want to donate some log data, I'd be happy to give you early access to that. Yeah, thanks for listening, guys. I know it's a short talk, end of the day, so I try to keep it a little bit more brief. So yeah, any questions, any follow-ups or anything like that? Yeah.
For the data that you said regarding solo mining, I know you said you didn't really dig into that much, but also that it was very heavy clustering.
Mm-hmm.
Do you happen to know that solo mining actually mined a block?
Yeah.
Probably not very likely, but
Yeah. So
very anomalous.
exactly. So the question is, when I was looking into solo mining, were any of the solo miners actually find a block? The answer is no. They didn't, and that is definitely something I should be doing to see what that traffic looks like for when a solo miner actually does find a block. If you're not into Cryptocoin mining, if that's not your thing, finding a block is extremely rare and quote-unquote difficult to do. That's why people do pool mining. So everybody pools their resources, and you all look for a block. And that's what I was talking about, submitting a successful share. You found part of a block, and your pool gets a payout, and you get a share of that full payout, depending on how much work you did. Whereas solo mining, it's all on you. And you're basically playing the lottery with far worse odds at that point. Far bigger payout, but far worse odds. But no, I haven't. Anyone else? Cool. Thanks, guys. Appreciate you coming out.